This is Bill Kinney, and I'm a professor of math at Bethel University, and this is a fourth video that I'm making about calculating integrals that arise in arc length calculations for parametric curves. Again, I would recommend that you take notes as you watch this. Pause it whenever you feel like you need to. Here's the formula that we're going to use, and once again, we're not explaining this formula, we're just getting some practice using it. And here's our problem. Let C of t be this parametric curve. First coordinate or component equal to t minus sine of t, and second equal to 1 minus cosine of t. And I'm going to dispense with first finding the arc length over a certain specified interval and then finding the distance traveled function. Instead, I'm just going to go ahead and find the distance traveled function right away and then use that formula that I get to find the distance traveled over the specific interval from 0 to 2 pi, the distance traveled at time 2 pi, meaning between the interval between time 0 and time 2 pi. Alright, so once again we'll just copy and paste this formula down here and plug in the derivatives of x of t and y of t. So there's x of t there, t minus sine t. I differentiate it. I'm going to get 1 minus cosine t. And here's y of t. I differentiate that. The derivative of cosine of t is negative sine of t, so the derivative of negative cosine of t is positive sine of t, though since we're squaring it, it really doesn't make much difference here. A is 0 and b is t, which means I really need to use a different letter besides t in the integral, and as usual I will pick a tau, the Greek version of t. Alright, so as usual now we want to simplify as much as possible. So in this case we have to square this out. If you think about foiling, F-O-I-L, first outside, inside, last, the expression, the binomial 1 minus cosine of tau, you're going to get 1 times 1 is 1. Outside times outside is going to be negative cosine tau, and then another negative cosine tau from the inside times inside to give you negative 2 cosine tau. And then the negative cosine tau times itself will be positive cos of tau squared. And then we just have a sine of tau squared, which I'll write in the more traditional way. I'll put the sine, the square, right there. And whenever you see this kind of thing, you're always happy because that can be replaced by a 1. And then you've got the 1 here to give you 2. And then the 2 can be factored out if you like. So actually, let me put this on the next line here. So we have a 2 here. Get rid of this. If you like, the 2 can be factored out. Not that you have to, but show you can do that. And you could take the square root of 2 and put it out in front if you like. This looks perhaps kind of difficult, though. What do you do to do this integral? Oftentimes with integrals involving trigonometric functions, you need to use a trigonometric substitution, some sort of identity. And the identity that's really useful in this case is that sine squared of an angle is 1 minus cosine of double that angle divided by 2. And in this case that's useful because you can replace the 2 theta with the tau. Multiply both sides by 2 as well. Replace 2 theta with tau. And if you do that, think about that, maybe pause the video, replace 2 theta with tau, that means replacing theta itself with tau over 2. And right, so now if you make the replacement, this is now going to get replaced with this, you're going to have a second 2, that's going to give you a 4 here, and then you're going to get the sine squared of tau over 2 right there. Square root of 4 is 2, so that can be brought out in front. And square root of sine squared tau, technically speaking, is the absolute value of sine of tau over 2. Smaller. Though we are focused on the interval where t goes from 0 to 2 pi, that means t over 2, or sine of tau over 2, where tau is between 0 and t, is going to be positive, because that'll be between 0 and pi, 0 and 180 degrees. So that means, that's why I made this restriction, that means I can get rid of the absolute value signs, and the integral that's left to do now is easy. So let's see, what will it be? Maybe pause the video again, think about it. Actually, I should get rid of the integral sign here. Integral of sine is going to be negative cosine. And the fact that you've got a tau over 2 inside there, let's see, means that when you differentiate, you'll get an extra 1/2. So I'll need a 4 there instead of a 2. Tau goes from 0 up to t. Double check maybe by differentiating this. Again, the derivative of cosine is negative sine. The negative sign here, no pun intended, is going to go away then, and you'll get an extra 1/2. That will make this 4 turn into a 2. This looks like I've done it right. Now plug in first t, and then subtract what you get when you plug in tau equals 0, which means adding a negative, or subtracting a negative, so you add. Cosine of 0 is 1. So ultimately here it looks like we get 4 times 1 minus cosine of t over 2, or you could multiply the 4 back through again, it doesn't matter. This would be our distance traveled function. Let's see if it's what Mathematica spits back if we do this. I'm not sure that it will be. Mathematica may spit it back in some equivalent form, maybe using some trig identity. I'll do this form of it here. It may not look the same, but probably through the use of some trigonometric identity, it should be equivalent, although there is the issue about Mathematica doesn't know what value of t to use here. Let me stop this evaluation here. I was saying t was between 0 and 2 pi. What would this mean about the distance traveled from 0 to 2 pi? This thing right over here, this is the distance function as a function of t. So from 0 to 2 pi, you're going to get 4 times 1 minus cosine of pi. Cosine of pi is negative 1, so 1 minus negative 1 is 2. You're going to get 8. Let's just go ahead and make this a 2 pi here and see if we get 8. We do. Okay, so that's some evidence that we probably did it right. Here's a picture of the situation. That's the parametric curve right there. This is actually a very famous parametric curve. It's called a cycloid. It comes from watching the edge of a wheel spin through space as the wheel moves along the x-axis here. And you'll get that kind of curve. The point on the edge of the wheel will follow that kind of curve. So I think I did it all right here. I'll just assume it and end the video there. Double check things, really think about it. It is a little tricky here, but is an important example.